8, 7, 6, 5, 4, 3, 2, 1, 0.
Yes, yes.
I kinda like you.
It was the beginning of a new century, and the whole world awaited a great change. Like any other place in the world, one such change was about to spark on the grounds of NITH. The person we will be hearing from today is the one who brought that change and gave his alma mater the legacy that we behold till date, in the form of our celebrated college magazine, Srijan. However, this was just the beginning of a journey which speaks of diligence and radiates brilliance at each step. Embarking on many more exciting ventures, our guest has always been an exemplary personage, an alum who keeps us hooked with his groundbreaking works and witty writings. Come on, who doesn't wait for his articles in the yearly editions of the college publication? We are very much delighted to call upon our screens Dr. Kumar Vijay Mishra, all the way from Adelphi, Maryland, to give us some stirring insights into this gripping journey of his.
Okay, thank you, Arsh. And thank you, everyone, for organizing this excellent festival. And my sincere thanks to the organizers and the NIT Hamirpur community for inviting me and giving this opportunity to me to talk about my research. So it's always great whenever I connect to my alma mater, NIT Hamirpur. And although I have studied in many other institutions, the kind of connection that I have with Hamirpur is just one of its kind. So with that, let me share my screen.
Sure, sir.
Okay, can you see the screen?
Yes, sir, it's visible.
Okay, so I'll just give some opening comments, and after that, I'm going to formally switch to my presentation. And I'll switch off my video during the time of the presentation so that we can just focus on the slides. So yes, I mean, Nimbus was not organized when I was an undergrad at NIT Hamirpur. So this happened, I think, probably a year after I left Hamirpur. So I'm very happy that we are continuing this tradition of organizing technical festivals at Hamirpur. And I congratulate the whole team and everyone who has worked very hard in making this a success. So I'm going to talk about not just about my journey to become a radar engineer, and I think Arsh gave a very nice introduction of mine, but in a nutshell, I'm only an engineer like many others, and I'm just a researcher like, again, many others. So I'm going to share my perspective about my field, how I chose it, and how I became a radar engineer. Currently I'm at a United States Army Research Laboratory. It's very close to Washington, D.C., the capital of the country. And we just had a very unusual winter this year, but today is a sunny day. It's kind of rare in March. So it's a very nice day, and I'm quite excited to start this talk now. So let's start, before I talk about more technical content, let's start about the nature of research itself. Why should one choose a career in research? Obviously, there are so many careers available, and especially in India, a lot of people go to do engineering, and then they turn to become MBAs or IAS, which has nothing to do with research, or sometimes even engineering. So why should someone pursue a career in research? After all, it was something that was a forte of people who were studying mathematics, physics, or chemistry. Those were the people who used to do research. And engineering departments especially electrical engineering departments, and in India we call it electronics, but here in the US, the electronics and electrical engineering, sometimes they are all combined under electrical and computer engineering. So when I say electrical engineering, it actually covers both stream, electronics and electrical, and sometimes even computer engineering, but not computer science. So no one should take an offense that I'm calling one particular stream as electrical engineering. It's actually very wide. So if you look into electrical engineering departments in the United States, they only started around late 1800s. So about 100 or 110 years, this is how the electrical engineering stream has been around. Especially after the work of Thomas Edison, the electrical engineering started taking off in a big way in the universities, while the research in mathematics, physics, and chemistry dates back even much before that. So a good answer why someone should do research all the time, if I have to give a very fancy answer, I will quote Aldous Huxley, who was an English essayist, and some of you might have even read his works. And he even visited India sometimes and has written essays on India as well. So he said that even if someone has a talent for literature or art, in his own words, even if I could be Shakespeare, then I should still choose to be Faraday. Although Aldous Huxley did not become a scientist, he became an essayist. But it's this fascination that he was of the opinion that one could contribute to mankind by doing more work in sciences or in research. So that is a good answer. But that's not how it happens in practice. When you enter the first year of engineering, then as this graphic shows, your goal is to win the Nobel Prize. And then as years pass by, and I hope no one goes into their fifth year as shown on this graphic. Everyone finishes their engineering in 4 solid years. And as years pass by, then you realize that actually this is really hard, and your goals, they go on declining from Nobel Prize to, by the time you're in third year, you just want a job. And by the time you're in fourth year and still looking for a job, you'll probably settle for something less, and so on. And if you're beyond fifth year, then all you want is like a meal. So this is how it happens. But it doesn't mean that you should give it up, because research is a very challenging field. It is, if you're not constantly adding qualifications to your career in research, then pretty much you'll be chucked out of that field. So research is a field in which we don't just learn for a small a duration of time, like 4 years or 5 years, and after that all you do management. Research is not like that. In research, you are constantly studying. Even today, sometimes I take courses on new topics while going to universities, or sometimes even online. And even today, many a time I have to read a lot of textbooks if I want to understand a new topic. So in research, you're constantly learning, constantly educating yourself, and that is the nature of the work here in research. When you start in your first year in engineering, and if you want to do research, it will be like that first year for all the years of your career afterward. So if you're interested in working on nice technical problems, if you're interested in reading, learning, and I'm talking about the technical content here, then yes, you must choose research career. But if you don't have inclination towards constantly educating yourself on technical topics, then this is not a career for you. So this is something that any early researcher must understand, that if you want to choose research, then be ready to read a lot of books, a lot of papers throughout your career. And we have researchers who are above 80 years. So like Eli Bruckner, who is the father of phased array radars, he still attends conferences and he's already 85. He still writes papers. And for that, he still has to spend time in reading, because in research, you can never call yourself that you're perfect and you know everything. The field is changing all the time and you have to update yourself all the time. How to conduct research? There was an excellent talk that was given in Bell Labs in 1986 by Richard Hamming for students who study electrical, computer, or electronics engineering. And maybe some of you might have also heard his name in your 11th, 12th textbooks on physics. So Richard Hamming, he devised error correcting codes. Hamming distance is also named after him. Hamming window in signal processing is also named after Richard Hamming. So he was a pioneer in signal processing and information theory research. And he gave this talk, which is titled You and Your Research, in 1986 to an audience in Bell Labs in New Jersey, which is not very far from where I am. It's a couple of hours drive. And in this talk, which I encourage all of you, the students, to actually read the transcript, and there is also a YouTube video that you can watch. But I prefer the transcript because it was written so, it was delivered so well that it almost looks like he actually wrote the whole thing. And in that talk, he talks about various aspects of research, how to get started, what kind of topics you should pick, what is the success to being a good researcher, and so on. And it's not just about the technical specializations that he is talking about in that seminar. He also talks about some of the personal characteristics a researcher should have. And he does not encourage people to work in isolation. He encourages collaboration in this talk. And he also says that even though we have the stereotype of scientists being very antisocial, in this talk he encourages a good social attitude to scientists and researchers, and how even a good social attitude actually helps in research. So it's a very long talk, but a very important part of the talk is this one sentence. He says, if you do not work on an important problem, you will not do good research, which is interesting because this sentence decouples researcher's own personal expertise from his or her success. So you may be a very good researcher, but if you do not pick an important problem, and if you're working on a problem which is probably very, very difficult, but it is not that important, then it is very highly likely you will not be able to do good research. Because most of the good research content or good research achievements, they have come from working on important problems that matter to humanity in general, or even to your own field. So many a time we don't know what is the significance or import of a particular problem to, in a larger sense, to humanity, but within your own field, it can create a very high impact. So you must choose an important problem to do good research, and that is the key. So this is what at every stage of your research career you should think about. Is the problem I am choosing, is this important? What kind of impact it will have? How many other people are working on it? And it's not like if no one is working on it, you should not choose it, because if the problem is important and still no one has touched it, then all the more reason to choose such a problem. Of course, you may not have any help in the beginning because no one has worked on it, but then whatever work you will do will create a good impact. So impact is very important in research. If you write papers which are not cited by other researchers, which create zero impact, then you're likely not doing very good research. On the other hand, if you choose a problem on which everyone is working, the challenge will be to carve out a unique niche for yourself, but at the same time, you will have a lot of prior work available on the topic. So in both cases, there is a potential to do good research and make a place for yourself. Another important point that Hamming stressed on in this talk was, which is something that I don't agree with, but he says that lot of great results in sciences, engineering, or in research, they came from people at a very young age. So if you look at Nobel Prizes in physics, chemistry, or medicine, or even Fields Medal in mathematics, which is given to researchers who are below 40 years old, then all those achievements were done by those people at a very young age. Like William Bragg was just 24 years old when he got the Nobel Prize, which means he got his PhD even before he turned 24. And there are countless such examples. On the other hand, in literature, in humanities, most of the big achievements have come when people are very old. So if you look at Nobel Prize for literature, that is given to authors who are quite old, and many of them they have received the Nobel Prize and they passed away 1 or 2 years afterward. So in that area, usually it's a lifetime of work, and the maturity in writing comes with age and so on. Of course, there are very young winners as well in humanities and literature, but those are exceptions. However, increasingly, this part is changing in engineering. So he gave this talk in 1986. At that time, a lot of people used to work alone. So if you look at Nobel Prizes in its early years, used to be given to, no one will share a prize. It will be given to just one person. And that was the case for many decades. But lately, we are seeing that Nobel Prizes almost every year, they are given to, they're shared between 3 researchers or 2 researchers. That is because the nature of research over the last 100 years or so has changed drastically, and now people do more collaborative research. At the same time, the problems, because the nature of the problem has become multi-disciplinary, it requires people to gain more expertise before they could make some significant contributions. And that's why I would not agree with Hamming that you should be very, very young to make a good contribution in research. And a very good example of this is Yitang Zhang, who is a mathematician at University of California in Santa Barbara. He completed his PhD at Purdue University in late 90s. After that, he could not get a job because at that time, the job market was not that good. So he could not become a professor. And for many years, he took on various odd jobs like a pizza delivery worker or a motel accountant and so on. But he never stopped working on his research, even in his free time, and even though he was so much detached from the technical or research community. And at the age of 57, he submitted his first paper after his PhD to Annals of Mathematics, where he came very close to solving the twin prime conjecture. So you guys can go online and look into what twin prime conjecture is. It has remained unsolved for many, many years, and a lot of people have attempted it, but they couldn't solve it. Yitang Zhang, who no one knew about him because he was not working in research. He submits this paper and he solves the weak version of twin prime conjecture. And he was 57 years old. So they couldn't give him Fields Medal because that is given only to people below 40 years old. But they called him as a distinguished speaker in the International Mathematics Conference. So that was the honor that was given to him, and he has received a lot of other prizes afterwards. So that is also an inspiration that if you want to make a good impact in research, the main point to stress here is you should constantly train yourself. You should have a lot of perseverance. You should work on the problems all the time. Maybe you may not get a result today, but you will get it at some time if you doggedly pursue that problem. So that is very important. This was the part that was not there in Richard Hamming's talk. So this is what I am telling you. So all nice. So it looks like the research is supposed to look like the diagram, which is on the left side, a very nice version that, you get data and then you do some measurements and then you get a prototype and then you write a paper. That is how everyone tells you it should be like this. But in reality, it rarely goes like that. It is more like a mess, like on your right side, the graphic on the right side. And these graphics are from phdcomics.com, which is quite popular among the PhD students. So research is quite messy because it is all about the unknowns. If you don't know anything about a subject and you are asked to solve a big problem in that subject, then you just don't know where to start. And that's why it cannot be a nice diagram like this. More likely, you will end up with reading multiple things which don't make sense. After a few years of training, then more or less it starts approaching figure one, but it never actually gets there. So this is something also that researchers should know about, that research is not a straightforward path. You try to find out a solution to one problem. You may not find it out, but in the process, you will learn a lot of other things, and maybe it will lead you to another area. So the reason I put this diagram here, because my journey as a radar engineer was also like this. I had not planned to become a radar engineer when I entered engineering. It just so happened over the time that I was working on one problem, and then suddenly radar became more interesting for me. Hamming also said in his talk that you should change your research topic every 7 years. I don't know how he actually came to this number 7, but this is what he said in his talk. And if that is the case, that we are to change our topic every 7 years completely, then you will be in this research mess all the time, because you will again start with unknowns, and then you will move on to probably a more structured way of doing research on a new topic. I don't really agree with, first of all, the 7 years. I don't agree with it. I think 7 has become 3 or 2 years these days, because problems are changing so dynamically, and I think the scale of research has changed drastically over past few decades. So I don't agree with that topic, and I don't agree that you should change your research topic drastically. You should pick up new problems. That's what I think he probably meant to say, that don't work on just one problem all the time, because research is changing continuously. You should pick up a new problem, but probably within the same area. So if I'm working on one aspect of radar today, maybe after some time that may not be of interest to the larger community, and there may be new things that would have come up. So I should move on to a new topic or pick up a new problem, so to say, after maybe 2 or 3 years. I think that is what he meant to say. So again, this underlines a very dynamic nature of research. Again, you cannot stick to just one problem for your lifetime, maybe unless until it is twin prime conjecture. But as engineers, we work on slightly different topics rather than conjectures. So what was I doing over all these years? So as you can see, in my first year, I went to Manali, and this photograph is from Manali. And this was probably during one of the vacation times in Hamirpur. In my second year, I was a member of Kailash Boys Hostel Cultural Committee. And again, I was spending time not studying much, but as you can see, this was in hostel night. So I was spending time in organizing these kind of events. In my third year, I was in English club. This is from Hill Fair, I think 2002 Hill Fair. And again, we were just having fun. In my final year, I was dancing. This is from Saraswati Puja celebrations in, I think, Mani Mahesh Hostel. So again, so basically, I was just wasting my time over all the years. So if Hamming said that I should actually change my research topic every 7 years, I should work on an important problem, I was not doing any one of those things. So that means I was going to be in deep, deep trouble because at least people like Hamming, they were doing research right from their first year in college. I was not that kind of person. And today, so we fast forward by many, many years, almost 2 decades. And today, this is where I am. So I'm a National Academy's Harry Diamond Fellow at the Army Research Laboratory. I'm also an Honorary Research Fellow at the University of Luxembourg's S&T Center. And apart from that, I'm also the Chief Technical Advisor of 2 startups. One is Hertzwell in Singapore. It is a startup on self-driving cars. And another one is Aura Intelligent Systems in Boston, which is, again, a radar startup. And a lot of things that you will see in these slides, that is thanks to all these agencies that have funded me, the National Academies of Sciences, Engineering, and Medicine, and then these other institutions that I just mentioned. And today my research interests are quite wide. I primarily work on radar with focus on both signal processing and electromagnetics aspects. I'm also working on communications theory and systems. And in general, all of these are covered under the umbrella of remote sensing applications. So from having fun in college to a more serious researcher today, how did it happen? So the first thing is you have to work with people who are experts in their areas. So it's very important to have good teachers and mentors because you need someone to look up to, unless until you are some young prodigy. Most of us need someone we could look up to. So very, very important to have good teachers, to work with the leaders in your field. So this is a sentence that I had in my thesis, Etain me nibandhe narpita vai guru dakshina. What it means is that through this composition of mine, I pay my obeisance to all my teachers. This was in the acknowledgement of my thesis, because I realized it after working on research that if you do not have excellent teachers, it will be very difficult to make headway in research on your own. There are examples, of course, where without any formal training, people have been able to make a big impact in their fields. For example, Srinivas Ramanujam did not have any training, formal training, and he made so many contributions in mathematics. But at the same time, if he was not called to England by another big mathematician, G.H. Hardy, if Hardy had not given him that opportunity, maybe we wouldn't have heard about Ramanujam at all. So even though Hardy didn't personally mentored him, he did give him an opportunity. Many a time, your mentors, advisors, and teachers, they may not be able to actively help you on a research problem, but they can facilitate opportunities so that you work on good problems and you get good exposure. So that is very important. And the second is you must have determination. So this is my favorite chaupai or a quartet from Tulsidas's Ramcharitmanas, which goes like Jo ichha kare hi ho man mahi hari prasad kachu durlabh nahi, which means that you should have some faith. So not just faith in God, but at least faith in yourself, some kind of faith and perseverance, so that you can continue pursuing your goals. And if you do that, then at least you will get some results. And research is a field where you must constantly pursue the problem. Otherwise, you're not going to make an impact. And if you don't believe in this, then as this screenshot from one episode of The Big Bang Theory says, that these are empirical evidences. I don't have any proof that both rule 1 and 2 will work for everyone, but it is an empirical evidence. And in research, we don't throw away any kind of evidence. We don't definitely throw away empirical evidence. Hard evidence, of course, is very important. And anecdotal evidence is something researchers don't like, but all kind of evidences are taken into account in research. So this is the empirical evidence that I have from my own journey as a radar engineer. So how do we study radar? Which is my current field. So it's a multidisciplinary field, and you can think of it as a very big river whose two feeding rivers are signal processing and electromagnetics. So in order to be a good radar engineer and researcher, you must have a good grasp of these two disciplines, signal processing and electromagnetics, because they really form the core of the radar. However, the actual picture of radar looks like this. It actually has a lot of feeding rivers, but they are probably smaller. Radar theory and applications in a lot of labs where I've worked, people with background in computer science, atmospheric science, civil engineering as well, who work on radar hydrology, physics, biology too, because there is a field called radar entomology, which is the study of insects using radar signals, vehicular technology, so mechanical engineers too, and mathematics. So a lot of these fields, they are quite disparate, but radar is that one unique field which brings all of them together, and it has so many applications that I've been sometimes surprised to find people with a very different background working on radar, like atmospheric scientists. They also work on radar. So if you want to study radar, should you study all of these? Probably not. I would say just electromagnetics and signal processing to start with, and you will pick up these other things with time. With more years you will spend in this field, you will be able to get a good grasp of its other applications too. So as I mentioned, I didn't enter engineering thinking that I will work on radar research. My first paper, it's not a research paper, it is something just like Nimbus, we used to have, at that time, we did not have Nimbus in Hamirpur. So the closest one was Literati Technical Festival in NIT Kurukshetra. At that time, it was called at REC. And one of my roommates in my second year, so we had no clue about research in second year, but I'm very thankful to my roommate, Rio Mascarenes, who is portrayed in this top photograph standing on the right side. This was taken in Kurukshetra. There is a small lake there. That's where this photograph was taken. So he suggested, okay, let's go and participate in Literati. And then I told him, but I mean, we don't know anything about research. So what should we do? He said, oh, let's just go to the library and start reading some papers, and maybe it will give us some idea. So we went to Hamirpur Library. And at that time, the internet search was not that popular. This was just 2000, and if we will go to downtown, we'll have to pay like 200 rupees. It was a lot of money at that time. 200 rupees for like 1 hour of browsing the internet. Luckily, the librarian who was in the NIT Hamirpur library, he told us, if you can tell me what to search, if you can give me keywords, I can send you a list of papers, and then you can go upstairs in the actual library and find those papers in those journals. So it's almost like you want to do Google search and you have to tell someone that, okay, can you search for this? And obviously that these days we do Google search iteratively. We search for maybe 100 things within 5 minutes on Google. So this was like a very painful process to tell the librarian that, okay, we are looking for these topics. Then he gives us a list. And the next day we go to the library, and then again we go to him, oh, this is not what we wanted, can you now search for this? And at one point of time he really got fed up with me and Rio, and he said, okay, why don't you guys search it yourself on my computer? And that is what we wanted. We wanted to search for papers ourselves. So that's how we started, and we started reading technical papers for the first time in our second year. And then this first so-called paper, it was essentially on a topic of how to apply artificial neural networks for smell detection. So different types of smells. So we called it electronic nose. We presented this in REC Kurukshetra, and we actually won the contest there. And this was just the second year. And that was my first real interface with research, even though it was not an original work, and it was nothing like we actually did some work or carried out any experiment, but just reading good research papers was the key to get interested on research topic. And then I worked with one of my faculty advisors in final year, Dr. Rajivan Chandel. I think she's still one of the faculty members in the ECE department there. And with her, I authored my first conference paper, which was on a VLSI topic. And I attended my very first conference. This was just the beginning of my final year and end of third year. In IST Bangalore, where I was very, very scared. I just went there alone, and I was one of the very few undergrad students from any NIT to actually present a paper there. And I was very scared because I thought, I don't know much about this topic. So in research, you always have a lot of self-doubt, even though you see a lot of successful researchers, but they all battle with self-doubt. So it's very common. Even if you have self-doubt, my suggestion would be not to give up, because everyone has those kind of feelings. And you should just continue working on the problem. So that was my first conference paper. And then I got really interested in research. Otherwise, at that time, I was considering other careers after my BTech. I was thinking about either preparing for IAS or do MBA and so on. But that's when I decided, after going through this series of closely related to research works, that no, I really want to do research. So in India, how do you do research? One is you either join a research lab or you join universities, probably do MTech or PhD there and so on. So with me, it was I joined the LRDE, which is Electronics and Radar Development Establishment, a radar lab of DRDO in Bangalore. And that's where, again, I got a very good mentor there. With whom I'm still in touch with. And he guided me towards working on radars. And that's when I seriously started looking into radar research as a career. But very quickly I realized, because as you have seen in the previous graphics, that radar is a highly multidisciplinary field. So very quickly I realized that probably I don't have sufficient training to become a successful radar engineer. So the 4 years that I was in DRDO, I worked on a lot of radar related hardware, very cutting edge hardware, which is still used by Indian Army in a few radars that are deployed along the borders of India. But I realized that if I don't get more education and I don't get proper training, I may not be able to make more impactful contributions in radar, because most of the time I may not be doing research. I may be doing mostly engineering, that is working on the hardware and making these radars. But I wanted to be at a place where I can come up with a radar design all by myself. I can choose new radar topics, and I can also influence radar research across the research community. For that, you definitely need a PhD. And but then how to get a PhD, that is also a very long process. So I decided, okay, let me first get my master's. So I went to I started in 2007 my graduate program in the United States. It turns out although radar is such an influential field even today, it is not one of the very popular fields. Most of the people, for example, today want to work on machine learning, deep learning. At that time, everyone wanted to work on communications or some other topics which are very popular in industry and so on. So there are very few schools in the US which specialize in radar research. So at that time, there were just few of them. And then another problem was that radar is a classified topic in the United States. So foreign nationals are not allowed to work on that subject. It is quite sensitive. So how could I get a master's and PhD in radar research if I'm a foreign national and I cannot work on those topics? And in LRDE, I was already working on military applications of radar. So there was supposed to be a switch. So when I did my master's in Colorado, then I did not work on military radars. I worked on civilian radars, that is weather radars which observe weather, which help in the forecast for meteorologists. So as I said, it's a very multidisciplinary field. So even meteorologists today, they rely on radar data. So it was a switch of topic, but having already said that you can change your topic in 7 years. So I changed from military radars to weather radars when I did my master's. And then this continued over my whole PhD program. Then I went to earn my PhD in Iowa, where my mentor told me that at the time I was working a lot on radar hardware and experiments. And he told me I'm not going to get a PhD until I make a contribution in theory. And in order to do that, because signal processing, radar signal processing is a very mathematical field. And at that time, I did not have a very good training on a lot of mathematical topics. So he said, why don't you first do your master's in mathematics? that will give you a good training in mathematics, and then you do your PhD in electrical engineering. So it was a shock because I thought, oh, I have to spend so many years now doing masters in mathematics, and I don't have an undergraduate degree in mathematics, so it's going to be hard. And after that, then I have to do PhD. So he said, no, don't worry, you can do both of them concurrently. So those 3 years in Iowa, when I earned my PhD in ECE as well as my masters in mathematics, are the toughest. But they taught me the most, actually. And I'm very grateful to my mentor who suggested me to also undertake training in mathematics, because both electromagnetics and signal processing, they are highly mathematical field, and it does help to actually have a training as a mathematician in these fields. After that, I had some brief stints at Qualcomm in California and Mitsubishi Electric Research Labs in Cambridge, near Boston, where I got a very good outlook of how the industry functions in the US. But again, I did not want to just work in industry at the time. I really wanted to be in radar research. So I went to Israel, Technion, which is almost equivalent to it's like the top college of Israel. So all the people who go to Technion later on, all of them, they go to MIT, Stanford, and these top universities. So Technion is a very good institute of Israel, and Israel has really good radar research. Their defense capabilities are one of the most advanced in the world. So I decided I'll go to Technion to do my postdoctoral fellowship. And Viterbi, which some of you may know, who has been the founder of Qualcomm, one of the founders of Qualcomm, and a great scientist, Viterbi Coding bears his name. So his foundation gave me this fellowship, and in the process, I also got to meet Viterbi when they were distributing this award, and that was very inspiring. So I did my postdoctoral fellowship there, after which I came back to the US at Army Research Laboratory. So currently, my research spans both theory as well as hardware, with a focus on radar applications. I develop algorithms for radar signal processing using latest advances in new theories such as compressed sensing or super resolution. I also work on development of prototypes, or that is hardware, which actually define my career for a very long time. Usually FPGA-based hardware design, as well as RF hardware and overall system engineering. And radar applications that I work on, they span a very, very wide variety of fields, from weather radars to radars for self-driving cars and so on, some of which we will see today. So what is my current research? So the current research is about how certain other systems, they interact with radars. So as shown on the screenshots from this series, Apple TV Plus series For All Mankind, which reimagines the space age by starting with that the first astronaut who landed on moon was actually not from the US, but from USSR, and then how things changed. So that is the premise of that story. And in one of its recent episodes, they talk about radiation coming from the sun, which is going to interfere with the broadcast spectrum on Earth. So the communication services, TV, radio broadcast, and all other kinds of communication services, they are going to experience this interference from the radiation coming from sun. So it's very real. That has happened earlier, because spectrum is a scarce natural resource. So if a particular service, radar or communications, is already using a part of the spectrum, and then suddenly there is interference or some other service starts using the same part of the spectrum, then there is going to be interference. So this is a problem that dates back to decades. It's not a new problem, but it has become more exacerbated nowadays because we have so many services. We have communications and radar working on all IEEE bands. So now it's an important problem. Again, you can see this radar and communications, even though they appear to be very different fields, but they actually operate side by side in many applications, and often they might even interfere with each other. So some of you may be a fan of this space science fiction series, The Expanse, which is, I think, on Amazon services, streaming services, where this is in the first episode where they're talking about that the sensor and comm arrays are offline for the spaceship. So sensor is which means radar, and communications. Their hardware is all together, and they have to keep it offline so that they don't get any interference. Then similarly, in another panel at the bottom, they talk about that probably the backscatter, that is the radiation coming back from a target, is probably not a radar radiation. It is actually a communication radiation, because this kind of interference can happen. So we had a lot of fun talk. Now we'll see a little bit, we'll get a little bit more technical. Even though this is at a graduate level, at a PhD level, I will try to simplify it as much as possible, but I'm not going to remove equations or theorems from the slides, although I will not go into a lot of detail into that. But just to give you an idea of what I'm working about, I'll keep it as I usually do in all my talks. So, the motivation for my current work comes from a recent spate of research and development of modern sensor-driven vehicles or self-driving cars, which you might have heard from Google car or Tesla's recent innovations. And these sensors on the self-driving vehicles, they are used to not only automate several vehicular functions such as driving, brake assistance, lane change, and parking, but also ensure safety through measurement of key health parameters such as tire pressure or driver's physiological behavior. So as you can see that the cars today, they are equipped with several different sensors, not just radar, but LiDAR cameras, and each one of them have their own separate functions. Now, in imparting autonomy and obstacle avoidance to self-driving cars, there are three major sensor technologies that are very common. First is a near-range camera, which has been on cars for a very long time. That was one of the first sensors that they had put on the cars. So a near-range camera, it provides a visual of the surroundings and some semantic information, but it is unable to measure Doppler velocity, or it is unable to function in harsh weather or low visibility conditions. Then you cannot get a photograph, right? LiDAR provides a very high resolution, but it is very expensive and it requires mechanical motion. Even though resolution is of high importance to self-driving cars, because resolution allows the car to differentiate between two close objects. So high resolution means it can differentiate two closely spaced targets. Low resolution means that the two targets might just appear as a single target. So LiDAR can help with that, but it requires mechanical motion. A radar is a cheap sensor. It is all-weather alternative because radar waves can penetrate through weather. It's microwave, so it can penetrate through weather. It can penetrate through some obstacles as well sometimes. And it directly measures Doppler velocity. So radar is actually quite critical these days in self-driving cars. And then integration of various sensors implies that modern cars have become increasingly software managed for not only in-vehicle functions like infotainment or gaming inside the vehicles, but also for inter-vehicular connectivity. So cars, in modern cars, they can also communicate with each other in some advanced cases. So I'm hearing some noise. This is... Okay, so as a result, because the modern cars, they can also communicate with each other. So there is also intervehicular connectivity that is envisaged in the next generation vehicular networks. And they do this to obtain additional traffic information or other entertainment options. So as a result, these connected and autonomous vehicles, they generate a massive amount of data, as shown here in a few statistics published by various industry groups, even though the cost of data rate and storage may go down. And if you look into current wireless technologies, they are unable to sustain this very high data rates. So effectively, cars need both high data rates and good sensing performance, which means it requires a good communication performance as well as it requires a good radar performance. And both communications and radar, in order for them to provide this high quality of service, they need very wide bandwidths. And from bandwidth, we come to the concept of spectrum. So if you require a very wide bandwidth, you need to access certain portion of the electromagnetic spectrum. But electromagnetic spectrum is a scarce resource, so it is difficult to satisfy the demands of both communications as well as radar. If you allocate more spectrum to radar, nothing is left for communication, and vice versa. And this is not just a problem with car applications, which are usually at millimeter wave, that is above 30 gigahertz and below 100 gigahertz. If you look into this chart, then pretty much every IEEE radar band has a coexisting interference source from a communication service. So VHF, UHF radars, which are usually foliage penetration radars, since 1980s, they are encountering this interference from TV or broadcast communications. Then weather radars at SC and X bands, they get interference from LTE communication devices. And today, with the advent of mobile and Wi-Fi networks, millimeter wave, which, as I mentioned, from 30 to 100 gigahertz, encounters lot of interference between communications and radars. And this is where the self-driving cars, they operate. So the solution to this problem, and people have been looking into this for at least 8 years or 8 to 10 years nowadays, is it possible that the radar and communication, they can share the spectrum, they can access the same bandwidth and operate without interference? So this is what we call as spectrum sharing radars or communication. So DARPA had a project on this, which is called S-Spark, which started looking into spectrum sharing radars at S-band, which is 2 to 4 gigahertz. And then it was expanded by other agencies across all bands in recent times. So nowadays we are interested in even terahertz band, which starts at 100 gigahertz. So what are the challenges? The first challenge is that is it possible that the radar could actually intelligently or cognitively sense which are the frequencies where there is interference and then transmit only in those frequencies? And then the second aspect is that how can we design such a system so that both radar and communications, they don't get interference from each other and they can operate with minimal performance loss. There are various ways in which the radar and communications, they can share the spectrum. So depending on whether the transmitter is common between radar or communications, or the receiver is common, or both are common, you can have various topologies. When radar and communications are completely separate, then we call it spectral coexistence. And when they share either the transmitter or receiver among each other, then it is called spectral co-design. So we just saw the motivation for joint radar communications. Now we'll quickly see how to enable this via the concept of cognition or intelligent sensing. And then very quickly, I'll mention some other interesting applications. So I talked about if the radar could intelligently sense the communications interference. And that brings us to the concept of cognitive radar. So there are many definitions of what cognitive radar is, but in general, there is an agreement that it is a system where both the transmitter and the receiver processing, it depends on the target scenario. So that means the radar should change something in the transmitter as well as in the receiver, depending on the change in the in its environment. If you look into conventional radars, then it changes only the receive processing, not the transmit processing. So this is a general definition of cognitive radar, and there are many interpretations, as I mentioned, but the one that we are interested in for the spectrum sharing problem is, can I thin the transmit spectrum? So if the radar operates, let's say, in 4 gigahertz bandwidth, and within that band there is a interference from communications, then could it actually skip that frequency and then transmit? That is what is called thinned transmit spectrum, and that is one of the solutions proposed for this spectrum sharing issue. And there are a lot of prior works on this, but most of the time they are very fancy and cannot be realizable in hardware. And a main issue is that if you actually put a notch filter at the interference, then the bandwidth, overall effective bandwidth reduces, and that causes distortion in the signal. And in radar terms, loss of bandwidth means loss of range resolution. Because more bandwidth means high resolution. So if you have notched out something, that means you're not using that frequency, and that will lead to loss of radar range resolution. So these have been some of the earlier works, and in our work, we address all these shortcomings by proposing a cognitive radar based on sub-Nyquist processing. What is sub-Nyquist processing? Most of you may be familiar, at least from second year onward, about the Nyquist-Shannon sampling theorem, which is one of the fundamental results in sampling theory and used a lot in electrical engineering. What it says is that if there is a band-limited signal, then you can sample in order to reconstruct a discrete version of that signal. In order to reconstruct a full version from the discrete samples of that signal, you must sample that band-limited continuous time signal at twice the maximum frequency. And this is an inviolable law. If you sample below Nyquist-Shannon sampling rate, then you will never be able to reconstruct that signal. And a lot of modern devices, they work on this principle. So in case of radar, if the bandwidth is large, it will give high range resolution. But at the same time, if the bandwidth is large, going by the Nyquist-Shannon sampling theorem, then you will have to sample at a very high rate. And sometimes the bandwidth is so huge, they go into gigahertz, that we don't have analog to digital converters to actually sample at those rates. So it's a real problem. I want to get high range resolution, so I want to use large bandwidth. If I want to do that, then I need high rate ADCs, but they are not available. So what to do? And then if a signal is sampled at such a high rate, then you have to carry out computations in your signal processor at the same rate, which is again imposes prohibitive costs on hardware, power, and other computational resources. So in 2006, a new theory was proposed by researchers in Stanford and UCLA, which is called compressed sensing. What it says is that it is actually possible to go below the Nyquist-Shannon sampling theorem and still be able to reconstruct the signal. For that, two conditions must be satisfied. First is that the signal that you are trying to reconstruct should be sparse. So as shown here, Y are the measurements, which is the vector on the left-hand side. And then X is the signal we are trying to sample. So X should be sparse, which means if it is a vector, most of its entries should be 0 and very few entries should be non-zero. However, if I sample this signal at a uniform rate, most likely I will just get zeros and I will miss the non-zero entries. So even though the first condition is that the signals should be sparse, the second condition then is do not do uniform sampling, but do random sampling so that you can actually get those non-zero entries in your sample. So A is the matrix which actually, which is a fat matrix. That means its number of columns are more than the number of rows. So if we do Nyquist-Shannon sampling theorem, this will be a square matrix. We'll be sampling everything from X, but in a fat matrix, you will sample just a few elements of X. And you can go below Nyquist-Shannon sampling rate. And then there are theories and methods on how to get X from Y. So Y are your measurements and how to reconstruct X from Y. It's a very established theory. And shown here is the book of my postdoc advisor who wrote a book on this topic of compressed sensing. So effectively, with this new theory, we could go below Nyquist-Shannon sampling rate and still reconstruct the signal. So all good. So can we apply this in radars? So that is the question that we pursued. And the compressed sensing based radars, there has been a lot of prior work. I would not go into details, but then they did not really address how to carry out this random analog sampling, or they did not consider all other kinds of cases. How does it perform in noise or certain other special cases? The solution that we proposed actually addresses the analog sampling directly. It is realizable in hardware, and it takes care of all these special cases too. And shown here is the hardware that we built. How does it work? So the radar signal model that we follow is as follows. We transmit, so in a radar, you transmit a periodic pulse train towards the target of interest. And when this electromagnetic wave, which is characterized by its phase, amplitude, frequency, and polarization, when it interacts with the target, then all these parameters of the electromagnetic wave, they change. And when it comes back to the receiver from the target, by monitoring the change in all these properties of electromagnetic wave, we can find out where the target is located, its distance, its size, at what velocity it is moving, its shape as well. So shown here is the equation of the transmit pulse train, and when it is reflected from L targets, which are characterized by these three unknown parameters, alpha L, tau L, and omega L, they all show up in the received signal equation, which is shown here. So here the unknowns are alpha L, tau L, and omega L, and we know H because we transmitted that signal. Now the question is how to get these unknown parameters from the received signal using fewer samples. And if you look into the classic pulse Doppler radar, this is a conventional radar that has been used since 1950s. It actually works on the concept of that you must sample the signal at its Nyquist rate and then carry out a bunch of computations before you can get all this information. And this is the principle that it follows, that if you have if you want high range resolution, you must transmit wide bandwidth and you must have a very high sampling rate. The sub-Nyquist theory or compressed sensing theory actually breaks the link between the signal bandwidth and the resolution. And how do we do that? So for that, there are a bunch of theories. The very first one was given by Martin Witterli at EPFL Switzerland, which is called finite rate of innovation. It allows us to model an analog input using very small number of unknown parameters. And if the signal is sparse, so the radar signal is sparse because there are only finite number of such targets in the sky. So it's not like you have targets everywhere in the sky, because then you can see them and you don't need a radar. If you have fewer targets in the sky, let's say L targets, then it is largely a sparse scenario because you don't have targets anywhere else. So such a signal can be modeled using finite rate of innovation theory. And if that can be done, then compressed sampling or exampling is a method that allows for sampling such a signal below the Nyquist-Shannon sampling rate. And then by using a few other tricks like Doppler focusing or compressed sensing, we then recover all these samples. And then there is a theorem by Bar-Ilan and Eldar, which actually tells us exactly how many minimum number of samples below the Nyquist-Shannon sampling rate are required so as to reconstruct this full signal. So as I mentioned, that the way this is done is that if you look into the Fourier series representation of the signal, then the Fourier series coefficients, they actually encapsulate all the unknown model parameters. So if I can get these coefficients, I can get these parameters, and that's what exampling does. It allows you to sample the Fourier coefficients, from which then solving a system of linear equations, we get all these unknown parameters. So that is for the unknown parameters, and then Doppler focusing is essentially, you can think of it as it transforms this two-dimensional problem where we have to find out both the distance, which is encapsulated in delay, and the speed of the target, which is encapsulated in the Doppler velocity, this two-dimensional problem into a one-dimensional problem. So it is one of the tricks, and usually this is accomplished using fast Fourier transform, as students of signal processing would know, but by operating on low-rate samples. So this is these are some of the equations. How do we actually accomplish it, which I'll skip right now. But the crux here is that after going through all of these steps, we end up with this final equation, which is a system of linear equations. But there is a problem. It is a system of underdetermined linear equations. So in your class 11th and 12th, you might have read about system of linear equations. And if it is undetermined, then there are infinitely many solutions, so you cannot find out the solution in that case. Compressed sensing tells us that you can indeed find out solution of an underdetermined system of linear equations if the solution set that you are looking for is sparse. So here, these are matrices H and V, but V is actually a partial DFT matrix, so that leads to underdetermined linear equations. And X is what we want to solve for. So typically, using normal linear algebra, X would have infinite solutions. But if X is sparse and there is a special construction of H and V, then compressed sensing allows us to find a unique solution of X. So this is a new theory that has become very popular since 2006. And that is what we use here for the radar problem. So far, so good. What we learned so far is that I can sample less in sub-Nyquist radar, and I can still reconstruct the whole signal. And I don't have to sample everywhere in that bandwidth. I can just sample some sub-bands. So instead of sampling this BH, which is this full bandwidth, now I just sample some disjoint sub-bands, and I don't make use of the whole bandwidth. So this connects the sub-Nyquist theory to cognition, because I can just transmit in those sub-bands where the communication system is not transmitting. And that's how I solve the problem of spectrum sharing. So conventionally, I was transmitting in this all band, which was interfering with these three communication bands. But now I am transmitting just in these radar sub-bands, which I choose cognitively. And then both radar and communications, they can work together within the same spectrum without any issues. And then now let's look at some of the theoretical results. So you can model both systems, and one system is using the full band, the other system is a superimposition of 4 bands. And then we have these questions: how to select these sub-bands in a cognitive radar? Having selected those sub-bands, how to allocate the power between radar and communications? And then how to, within a radar, how to give different power to different sub-bands. So in order to answer this, we actually resort to many different theories from literature. How to select cognitive radar bands, we answer it using the graphical sparsity theory. To allocate the power or the bandwidth between radar and communications, we answer that using game theoretic constructs. And then we turn to estimation theory to actually find out how to transmit the power across all subbands. So for the first question, if I have no prior information about RF interference, then choosing the subbands in the full band spectrum, it actually translates to choosing a group of rows in a DFT matrix or a discrete Fourier transform matrix. And in order to do this, there are certain theories which say that you can choose these rows, so that a special property of the matrix, which we call as mutual coherence, it is closer to another famous bound, which is called Welch bound. So there are algorithms to do that. However, if I do have information about RF interference, which you can find out by just observing the spectral interference over time. So if I know that this green thing, if I know their locations, where they are, then I want to position my subband such that overall interference is the lowest for radar. In order to do that, we had this paper in 2018 where we turned to a concept of graph sparsity or block sparsity. So I again won't go into a lot of details in this, but I just want to give an idea of how it works. So essentially, you search for a block sparse vector. So we just saw what is sparse vector. Sparse vector is a vector where most of the entries are zeros or noise, and very few entries are non-zero or signal. In a block sparse case, the non-zeros, they occur in blocks. So that's what we call it, block sparse. So essentially, in this algorithm, we search for a block sparse vector to find out the location of these subbands so that there is minimum interference to the radar from communications. For the power allocation, we turn to game theory. And essentially, in a game theory, it requires three things. First is you need the number of players. So in our case, there are 2 players, radar and communication. You need the strategy space. So where should the game take place? So here we are looking into the power that is allocated to both radar and communications to transmit them. And we want to see how much power should go to radar and communications, again, so that the interference is lowest. And then we need some utility functions in game theory. So for example, here it is the difference between the maximum signal to noise ratio and the minimum power. So by combining these 3 things, in a game theoretic framework, radar and communications are 2 players, which will now try to find out the optimum strategy space in order to optimize their utility functions. And there are many games that are usually proposed in this problem space. There are unilateral games where radar and communications, they just don't communicate with each other, and they try to maximize their payoffs. Or they can have some information from each other, which we call it symmetrical games, and so on. And usually the solution is given by one of the equilibrium condition. For example, in this 2% zero sum game, that equilibrium is the Nash equilibrium. So this is how the power allocation could be determined. And for the third question, how to transmit this power across different subbands, we turn to estimation theory, where there is a metric or a benchmark called Kramer-Rao lower bound. So Rao is an Indian scientist. He's 100 years old. He turned 100 years old this year. He lives in Hyderabad, India. And this very famous Kramer-Rao lower bound is actually named after him. And Kramer was another scientist outside India. So we find out Kramer-Rao lower bound for different parameters. And if the Kramer-Rao lower bound is it goes down, then it is termed as a good performance. So we had this theorem for Kramer-Rao lower bound for cognitive radar, and we showed that by comparing the Kramer-Rao lower bound of cognitive radar and the conventional radar, you can find out how much power you should allocate to each subband. And then what is surprising about this result is that we used less bandwidth than the conventional radar system, transmitted in disjoint subbands, did not lose a range resolution, sampled at low rate, and yet the Kramer-Rao lower bound for the cognitive radar could be lower than that of the conventional radar. And then you can sharpen this result by further looking into another bound, Zeev-Zakai lower bound. So Zeev-Zakai, they were professors in Technion, where I did my postdoc. So by looking into this additional result, actually you can sharpen this result even further. So we have also developed prototypes for this that we have demonstrated in various conferences on how to do spectrum sharing between radar and communications. This what we saw was a single antenna version. You can extend it to multiple antennas as well, and that's what we call in this phased array radar or MIMO radar. So it can be extended to multiple antennas, or you can look at it as application of some Nyquist theory in the spatial domain. So far we saw its application in the spectral or temporal domain, but you can also extend it in the spatial domain. So I will not go into these details. The concepts are similar, but instead of 2 dimension, now we are working on 3 dimensions. As you can see from these equations, they don't have 2 summations. Now they have 3 summations. But again, the concepts are very similar. You look at the Fourier coefficients, they have all the unknown parameters. And then instead of having a system of linear equations, now you have a matrix version of that equation, which you solve to actually not recover a sparse vector now, but a sparse matrix. And the whole concept can also be extended to cognitive array radars, which is my 2018 paper published in Transactions at Aerospace and Electronic Systems, of which actually I'm an associate editor now. All right, so far so good. Very quickly, I'll explain an interesting application of this compressed sensing theory to weather radars. So there is a concept of dwell time of radar, which means the time the radar beam or radar signal it spends on hitting a particular target. So you can think of it as that it is a dark night and there is a figure standing next to a lamppost, and you're very far from that figure and you're trying to figure out whether he's a stranger or he's your friend. If you look at that friend closely for some, at that figure closely for some more time, you might be able to figure out who that person is. But if you have just one look at that person, maybe you may not be able to find out if that figure is your friend or some stranger. So same thing with radar. If the radar looks at a target or essentially sends signal at a target or hits a particular target with electromagnetic wave for a longer time, then it is good for the radar. It can make accurate estimate of about the target. But if it hits the target with just one pulse or two pulses, then it may not have enough information. This is a classic definition of dwell time. Now, if we look at weather radars, which are constantly monitoring the weather, and there could be storms or tornadoes, then the next radar network, which is the weather radar network of the US, it takes about 14 minutes to complete one scan. But then certain storms or tornadoes, they do not last for more than 10 minutes. So essentially, if the radar is looking in another direction, then tornadoes could just pass that area. And by the time radar comes back to that location, tornado has already done the damage. So essentially, it's a very long time currently for certain weather phenomena for NEXRADs to take 14 minutes to complete a scan. So radars, they need to have faster update. That means they should scan very fast so that they are looking at all directions all the time. But then if the update rate is fast, the target accuracy will come down because radar will spend less time looking in a single direction. It will be looking in all the directions, but then in a single direction, it will be less time. So the target accuracy will come down. And if it does it slowly, then the target accuracy will be enhanced. But then the update rate is slower and the tornado might just pass by. So it's a contradiction. So how can we get faster updates and without compromising the target accuracy? So again, this goes back to compressed sensing. If I can take fewer samples in each direction, I can do faster update. And then I use compressed sensing to reconstruct the whole scene from the fewer samples. So in the weather radar, actually, very quickly, what is the principle? And if you look at the raindrops, and this photograph is from one of my mentors' papers in 1970, Wakimato and Bringi, and Bringi has been one of my mentors. In their paper, they took the photographs of falling raindrops. So raindrops are not these spherical size or a teardrop size as it is painted in classically when we were children, we used to paint raindrops as a teardrop size. But raindrops are not like that. In practice, raindrops are of these sizes, they are oblate, which means their horizontal dimension is larger than the vertical dimension. So that is called oblate. And when the vertical is larger than the horizontal, we call it prolate. So falling raindrops are actually not spherical or teardrop, they are oblate sizes. So this is the property that weather radars, they exploit by using polarimetry or by transmitting more than one polarization. So as I mentioned, electromagnetic wave has these properties: amplitude, phase, frequency, and the fourth property is polarization. So in a horizontal polarized wave, the orientation of the wave is horizontal with respect to the Earth's surface, and vertical can be defined similarly. So weather radars, they transmit two polarizations so that they can measure both the vertical and the horizontal dimensions of the raindrop. So that is the conventional radar, which transmits just one polarization, but then raindrop is oblate, that is horizontal and vertical dimensions are not the same. And in order to exploit this property, we use the dual polarimetric weather radar, which is what my advisor, Professor Bringy, invented in 1970s, and now it is used all across the US. In India, currently the radars are still single polarization. They have not been upgraded to dual polarimetry yet. And if you do that, if you transmit both, you can have measurements in both horizontal and vertical dimensions. And that tells us a wealth of information. It can tell you about the size of the raindrops. It can tell you about the density of the rain. And then all these parameters are used by meteorologists to make a forecast about how much rain is actually occurring or how much rain will occur in the near future. And these are the radars that I actually worked upon throughout my career, started from S-band at Colorado. So the good thing about the universities in the US is that all these advanced equipment, they are available to students to actually conduct their research. So I used to drive this X-pole radar or X-band radar throughout the university to make measurements. So it was just available to me and I could make measurements on this. So for this particular study, I used this X-band radar that I could drive around. It was fitted on a trailer on the back of a truck, and I will just take it to wherever the rain is occurring in my home state and just record the data. So same question. So I think compressed sensing, can we use it or not? So the first thing we have to check is whether the signal is sparse or not. If you look into the normal point target radars, like the radars that are employed at airport, there the signal is sparse because each red dot is an aircraft here. And then this radar is scanning this whole 360 degrees. Within that, it only has finite number of targets. But in weather, it is not the case. It might be raining in certain areas, or it might be raining everywhere. So what you are seeing here is a radar image of a storm. And all this, the red part is a stronger storm and the blue part is a very light rain. So it might be raining everywhere. That means the signal is really not sparse in spatial domain or time domain, or even in frequency domain, it is not sparse. So if you don't have sparsity, you cannot employ the classical compressed sensing. So how can we sample less and still reconstruct? That was the problem. For that, we turned into a new theory of matrix completion. So if I show you a matrix where I show only a few elements of that matrix, and then I ask you to perfectly guess all other elements of the matrix, can you do that? In general, we know it is not possible because if I show you a 10 by 10 matrix and I've shown you only 3 entries of it, which we call as partially observed matrix, there is no way you can guess all other entries. However, this new theory of matrix completion says that a partially observed matrix can also be used to actually complete the full matrix, as long as the rank of the matrix is low. So that is a sparsity in the matrix domain. A low rank matrix can be constructed perfectly from just partially observed entries. and you have to sample it randomly over this. So this was applied in 2008 in what we call as Netflix problem, where the rows are the movies and columns are the users. So any user, a user watches only a few movies and gives it a rating. So none of the users is actually watching all the movies on Netflix. So if it has observed 3 movies, it gives some ratings to those 3 movies, and other users, they give their own ratings to other movies. Netflix is in the process of making money, so it would like to recommend to the user that, okay, you have watched these 3 movies, like Godfather 1 and Godfather 2. Would you like to watch Godfather 3 also? So how would Netflix do that? So in order for Netflix to do that, it must complete this matrix. So since we know that a lot of users have very similar choices, or at least one particular user may have a lot of similar taste in movies, so that can make this matrix low rank, because if the columns and rows are correlated, then it can contribute toward bringing the rank down. So if it is low rank, then Netflix can complete the whole matrix and then start suggesting to the user that, okay, you haven't watched this movie, but this may be of your interest, so we are suggesting this movie. So this is how matrix completion was devised. Now we are actually going to see how I can use this matrix completion to actually address the weather radar problem. So we saw that, okay, it is possible to reconstruct the matrix, and how it is done that, it is done by what we call as nuclear norm minimization, another theory that came out in 2008. We won't go into a lot of details on this, but this is the method to actually reconstruct the matrix. So next question is it possible that the weather radar data is low rank or not? So we look into that. So if I arrange this whole weather radar data as a matrix, that means I transform it in a matrix, and then I look into its singular values of the matrix. So usually, as we see, this data is not sparse in the spatial or time domain, but if I look into the rank and I plot the singular values, then I can see that very few singular values, probably like 20 singular values out of 400, they are of higher values, and rest of all of them are very low values. So this is when most of the singular values are very small, then this is called a low rank matrix. So weather data is indeed low rank. It is not surprising because it's a connected system. If it is raining heavily in Hamirpur downtown, then maybe if you go a few kilometers away from it, then also there will be rain, and probably of the same intensity, and it gradually dies down as you move away and away from any location. So it's a connected system. That's why it is low rank. So we actually looked into that a little bit more in detail, that if we use all singular values, then this is the image we get. If we use 40%, very close to the first image, and of course when it is very few, then you can see that certain features are no longer available, but at least half of the singular values, if I take the data, they are actually very similar. So we did this reconstruction. You start with the full image, then partially observe it here. So we only sample few points, like almost 1/12 of the samples were taken, and then we reconstructed it. So this is how we extended to weather radars, and then we have worked a lot on this joint radar communications for self-driving cars at millimeter wave band, where we have extended this to many different cases. So here the radar transmits a communication signal meant for this receiver in gray, and then it is also transmitting. The transmitter is also sending a radar signal to find out the location of this blue car, and then another car. It actually receives both the message from the transmitter as well as it receives the location of T2 car in this automotive joint radar communications. This is our 2019 paper published in IEEE Transactions on Aerospace and Electronic Systems. It is one of my highest cited papers, which actually introduced the concept of joint radar communications to automotive applications. The different, what are the challenges for this millimeter wave or automotive joint radar communication, the biggest challenge is to find out the waveform which can do both. It can do radar functionality, and it can also do communications functionality. And we explored some of these in this work, like PMCW or OFDMA are the waveforms that we suggested here.
I'm really sorry to interrupt, sir.
Of our
I guess our
research.
audience have
How to do rainfall estimation, because not every area of the world actually has a weather radar. For example, in India itself, I mentioned that we have only single polarization radar, and most of them are on the coast, and some parts are still not covered. And in other poorer countries in Africa or in South America, they actually don't even have a weather radar, but there are storms there. There are all kinds of extreme weather phenomena that endanger human lives. So how can we get a good weather estimate in those places without installing a weather radar? So it turns out communications is not a nuisance for the radar in this case. It can help. So what we can use is that nowadays there are mobile towers all across the world, and there are more mobile towers than weather radars. So can we use the signal that comes from the communication satellite to the mobile towers, and it passes through the atmosphere. As it passes through the atmosphere, it loses its strength, or in other words, it gets attenuated. By measuring the amount of attenuation a communication satellite signal suffers while reaching to a ground terminal, we use that attenuation to find out how much rain would have occurred in that place. So this area of research is actually becoming very popular these days, and we have some work going on it where we are using deep learning and machine learning networks to actually reconstruct rainfall maps. As you can see here on the left side are the rainfall map constructed from this attenuated signal at the mobile towers, and that is compared with a radar. So of course you cannot get exactly what radar sees. Radar is more accurate, but if you don't have a radar, then at least this rough estimate that you can get from the communications user terminals can be very helpful in cases where there is no radar coverage. Finally, so I mentioned that I'm a chief technical advisor of this startup, Hertzwell, based in Singapore, where we are developing hyper-resolution imaging radars. And we have a lot of vendors from big automotive companies that are part of our initiative. And we actually make these automotive radars for self-driving cars for them. So this is based in Singapore. My current research in the Army Research Laboratory is focused on what we call as large intelligent surfaces. If you look into conventional communications or radar wireless transmitter, it has the antenna array, and then it has all this RF chain and a digital processor. The intelligent surfaces, which is again one of the very recent developments, it actually combines the RF and antenna together. So instead of using all these filters, mixers, and power amplifiers, that part is actually combined in the antenna array itself. And this so-called meta surface is what we call as intelligent surfaces. And we are looking into using meta surfaces for various applications in radar and communications. Because it can combine both RF, the analog component, and the antenna together, it actually has many interesting applications. For example, I can use the same surface to project multiple beams in different directions using the same array. Usually you cannot do that. I can also use the same surface to actually carry out different types of modulations with the same hardware. The same hardware can do OFDM modulation, it can do space shift keying, it can do spatial modulation, all those things, because here the antenna has become programmable. So this is one of the recent ongoing research topics of me. I would like to acknowledge several of my mentors and collaborators and all these agencies who have funded my work over the years. if you're interested in more details about my work, then about my recent work, then in IEEE Signal Processing magazine, I authored this overview article about my work. There was a book that was published in 2019 by Cambridge University Press, where the first chapter of that book is written by me, which talks about some Nyquist radar. I often conduct tutorials all across the world in various flagship conferences on signal processing and radar. And this year, I'm doing tutorials in ICAST and RadarConf. I have 3 books that are going to be published later this year and early next year. The first one is on signal processing for joint radar communications, to be published by John Wiley and Sons. So please watch out for that. And next year, 2 books are coming out to be published by IET Press and Arctic House. One is on the next generation cognitive radar, which we discussed in this presentation. And the third one is on modern SAR signal processing. So I didn't talk about SAR today, but maybe some other time I'll talk about it in future. So there is this book that I'll have. And at Hertzwell, we are always looking for students who are very good programmers, who are good in mathematics, and are in their MTech or PhD stages. So there are a lot of career opportunities and internships that we have at Hertzwell. If you're interested, send your resume to this email shown here, and maybe someone in HR will look at it if you're really good. With that, I would like to thank all of you for being such a patient listener. And again, thank you for the opportunity to virtually visit you and talk about my research. Thank you very much.
Thank you so much, sir. It was an enlightening experience for all of us, especially those stories which took us back in time. And only thing I could say is it was wonderful. So I see that we have some questions from the audience over here. And if you permit, can we ask those?
Yeah, please.
Yeah. So I see a question over here. It says that the research aspect in India. It says, sir, it is often heard India has a research deficit. What strategies do you recommend for improving the quality of research in India?
Okay, that is like a question that I'm afraid I'm not very equipped to answer, because I'm not any minister or heading any big agency in India. So I can just tell you from my perspective, I think we need to invest more on higher education. For example, we have to improve the quality of PhD programs significantly in India. Because when I came to the US, what I discovered is the undergraduate education in the US is not at the same standard as the undergraduate education in India. The undergraduate education in India and China and even some Eastern European countries is very good compared to the US. Because I would say undergrads in engineering in India know a lot more mathematics than, let's say, undergrads in the US. But the moment it goes to master's and PhD program, the US students, they just take over completely. There's a huge difference in the quality of master's and PhD programs. And that happens because of the resources that are available here in the US. And that investment has been done over decades. It's not new. For example, I had a radar at my disposal that I could drive around and collect data. In India, universities don't have access to radar. So the radars are with DRDO or ISRO, but not the universities. So we need to considerably invest in PhD and master's program, so that I think in theoretical research still there are good programs in India. There are good institutes where theoretical research, they are still very good. But then like mathematics or, if you're just working on certain theoretical problems, but the moment you need hardware or any big resource, for example, in certain universities in the US, physics students have access to a nuclear reactor. They can actually conduct experiments there while writing their thesis. In our case, to think about that, a university student would be programming a nuclear reactor will give a heart attack to everyone, because we don't have those kind of resources available to universities. So I think that is definitely needed. We need to invest in higher education, and it's a lot of factors are at play. But at the same time, a very good example to look at for us is China. So China became independent almost at the same time as India, and then if you look at what progress they have done, it's tremendous. 20 years ago, when I used to read papers from China, their English was not good, like all the usual problems, or the research was copied from somewhere. We used to see all these issues 20 years ago, so not very long. But today, Chinese researchers are literally publishing 50% of the technical papers in almost all major scientific areas. The English is no longer a problem. They are writing perfect English, and the results are also very good. And they have a lot of high profile researchers there who are now editors of journals. So they have really worked on it, and it's very hard work that the whole scientific community there has done. So it's not like we cannot do it. There is a country just next to us with very similar resources as us, became independent at the same time, and has done it. So I think if India continues to invest in higher education and research in a similar way, we can also reach there.
Yeah, that was wonderful. We need to make changes here. So the next question I'm going to ask you, it's like a lot of people from NITH have been wanting to ask this. So, starting anything new is always full of challenges. There's a lot of things to figure out between envisioning something and, then you have to pitch the idea to someone, you have to make them understand. And then finally, you see things coming around into reality. So what was the story behind starting Srijan at college? And when did you decide you wanted to do this?
Yeah, so I go to Aldous Huxley's quote where he says, "Even if I could be Shakespeare, I should still try to be a Faraday." But in the end, that was all talk, right? He eventually became like Shakespeare. So, like I said, I had no idea about research, and I've always been interested in humanities, in the reading literature. Although I hate to admit, I have not read a lot of fiction books in a very long time. For quite some time, I'm only reading research papers and technical books, or writing technical books these days. But at that time, you must have some objectives. If you cannot do research, do something else at least. So like I said, I did not get much exposure to research at that time, but I was interested in a lot of other things. And at a young age, the whole world kind of opportunities, the whole world is open to you. You can do whatever you want. Now, of course, I cannot spend time on pursuing a number of my hobbies, and they are gradually becoming zero or negative. But at that time, when I was just starting out, I wanted to try out everything in college. So I was a part of English club. I was a part of a lot of other committees or other activities. But I always had interest in writing, which has helped me enormously later in research, because as a researcher, you have to write a lot of papers. Of course, the content is completely different. It's a theorem or equations. But then an interest in writing, at least writing the introduction, is not all equations, right? But still, it's good writing really helps. So I would say my time at Srijan helped me a lot in improving my writing, although the nature of writing is very different than writing for a magazine and writing a research paper. But overall, you learn a lot in writing it. So Srijan happened because of just this general interest in reading books in humanities. And I would say all of us, if we get time, like Richard having said, that you should not be antisocial, and you should not just constantly be doing only technical work. The modern day researchers are multidimensional. But it was the case throughout the history also, right? Leonardo da Vinci was into so many things, not just science, right? I mean, he was a painter. He was doing a lot of things. Einstein used to play violin. So, everyone had all these different hobbies. But are they really disconnected? So, if you read this book, Gödel, Escher, Bach, right? So, Gödel was a mathematician. So it's called GEB. Some of you might have even read it. It got the Pulitzer Prize also. I think the writer of that book got the Pulitzer Prize. So Gödel was a mathematician, Escher was a painter, and Bach was a musician. Seems like very different things, but mathematically they are all connected. Music, as per the author of that book, is very close to mathematics, because in Bach's compositions we can see some mathematical structures. Painting by Escher, where he was painting all these impossible objects, some of which are featured in this movie Inception, right, which is where the characters they dream. So some of these impossible objects, like Penrose triangle, all those things, they appear there. So MC Escher was painting these impossible objects. So these things are not that much disconnected either. When you're young, you're exploring the world, you must try out new things. I mean, when I was a very early researcher, I used to attend talks on so many topics, even though I did not understand them. And even today, if I see that I can attend a talk, a technical talk, and it is not related to my field, I still go there, because you have to keep your eyes and ears open to new things all the time. And maybe with time, you'll learn it. So if we go back to college, then it's... I just wanted to do different things at that time, just to remain engaged, and I also wanted to contribute to the college. And when I realized that it doesn't have a college magazine, which I realized in my very first year, then I thought, okay, this is something to work on. And I worked with our faculty coordinator, who at that time was Dr. Saroj Thakur. Is she still there?
Yeah, she was with us last year, but I guess the faculty in charge has changed this year for Srijan.
Okay. Yeah. So, so she was there, and she encouraged me to actually do this. And we had a very good team. So the first thing that I did from my first year was to actually find out who all are interested in literature and reading books. And we just kept on, making that team. And that's how it happened. So just like how Nimbus happened, Nimbus was also started by students gradually. So if you think something is missing, then at your age, you should try to fill that gap. And most of the universities around the world, if we see, most of the initiatives are student driven. I mean, if you look at Harvard Lampoon, which is the Harvard newspaper, started by students. So everywhere it is like that. So NIT Hamirpur is not a special case. If you want to change, you have to be the change, as goes the cliche. But it is in practice everywhere. When I was in my third year and final year, I visited a number of IITs and IISc as part of some conferences, and I noticed that a number of societies in those places, they were started by students. Like in St. Stephen's, they have the PG Wodehouse Society, probably the only such society in the world, started by students. Shakespearean Society is started by students. So if everywhere else students could do it, why not we can't at Hamirpur? Of course, we are not going to start a Shakespearean Society. We are a technical college. Maybe you can start a Newtonian Society. But it has to be done by students. And initiatives which are taken by the students keeps students interested, and they go on for a long time. Because nothing is imposed on students. If someone comes and tells you that a faculty member, so to say, or if I tell you, why don't you start, society on blah, 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 then most likely it is not going to work out, because probably there is no interest, and you definitely need students to be interested in that, not just from your batch, but the following batches too. So, and it is developed over the years. So Srijan was there, but then I wasn't sure if it will be continued or not. But we recruited a very good team of third year, second year, and first year students, and that team continued it, and happy to see that it has continued.
Yes, yes, indeed, it's going really well these days. The Srijan is one of the most prestigious societies of the college right now. And there's one more
Glad,
question. Like you were the, sorry,
glad to.
sir.
I said glad to hear that.
Okay,
That
okay,
doesn't
yeah.
mean, I don't like other societies. So, but it's just that yes, Srijan is something special for me.
Yes, sir. It is indeed special for us as well. And one more thing, like you were the founding members of the Srijan. So, out of all, how did you come up with the name? Like, why did you call it Srijan? Why not something else?
Uh, no, there were a lot of names that were considered at that time. I think I wrote an article also in Srijan about this. That how did we choose the name? So number of names were considered over the years. Like the Wall magazine was called Prerna. Then we had Vichar. All these things were considered, but we wanted something new, something catchy, something that fits the bill of a college magazine. Someone also suggested some other technical names, but then it is really not technical. It's
Yeah.
really technical once we have IEEE transactions, right? So it's not a technical journal either. And yeah, so there were a lot of names and a lot of discussions. I mean, in Srijan, we used to have lot of discussions, and no one used to call sir or madam within the Srijan team. We'll just address each other by names. Even the first year students would call me KBM. So it was really a very constructive and open atmosphere. And within that, we'll go around, we'll ask for suggestions, and it was a very long process. So it didn't happen just like that. But finally, we had a list of about, I think, 8 or 9 names, and one of my batchmates, he was a really good critic. Sometimes just like that, like very annoying, but I'm very thankful to him. But I checked this list with him, and he'll just keep on striking down a lot of names, and I'll say this is a really good name, but say no, like, and he was not at all interested in literature. So I'm happy that
Okay.
I had a discussion with someone who was completely not interested in literature, because I wanted a name that sticks with everyone, not just people who are interested in that. And then we had like we had boiled it down to like 5 names or something, and then I met Saroj madam, and my preference was Srijan. But if you suggest just one name to someone, then it's difficult, right? So you suggest like 5 names, and then you see what is the reaction. So I suggested these 5 names, and she also picked Srijan. So maybe the other 4 names were deliberately not that we had not kept them like as good as Srijan. But so that's how it happened. It was lot of consultation and discussion. It was not like like I just came and decided it. It was not like that.
Oh, that was really wonderful to know. And as you talked about work culture, that work culture is still defined in Srijan. The work culture, it's totally different from other places, and it's the culture, it's still carrying on. So, do you have any message for Nimbus this time?
Okay, I guess you guys have done really good job. I mean, one message is, okay, keep calling me. Okay, that is a joke. So
From
no, so
Srijan, we will keep calling you.
I would say that you should expand yourself a lot. I think all of you are doing really good work. I saw the website, excellent. There are a lot of excellent contests that are being organized. Try to keep it as technical as possible, and also the organize contests which actually orient people towards research, because that is what Nimbus should do. For everything else there is hellfire. So try to make it more technical. Invite speakers who work on research, or even who have their own startups, because that is also important. Entrepreneurship in research or engineering, that is also one of the things that students of our institute should look into, right? So yeah, call people from various disciplines, from research, even people who are MBA. I mean, I'm not against MBA at all. Engineers doing MBA, they are doing good work also. Call them also, especially if they are from some technical field like finance or something like that, because those fields are also, they also require mathematical training, and they can also be very useful. So yeah, just expand yourself as much as you can. I mean, the best day will be the one. So I remember when I was in Hamirpur, and in Times of India, on the front page, on the lower right hand side, was an advertisement of Mood Indigo, which was IIT Bombay's festival. We have to reach to that level. We have to reach to the level where Nimbus, Hillfair, they are talked about, nationally at that level. So, which is very much possible. We have to just work very hard toward it. Like certain college magazines, they have become so famous, like Harvard Lampoon, and of course that is Harvard. It has a lot of exposure. But even within India, there are certain college magazines which are very famous. There are certain technical or the cultural festivals that are talked about in newspapers, in national newspapers. We have to reach to that level, and that is only possible with the good quality of the festivals and the contests. Invite speakers. I remember that someone in the Srijan team, he was a first year student. He said, "Why can't we put a message from the President of India in the magazine?" And everyone was like, "Oh, that is not possible. We are too small for it." I said, "No, it can be done." He sent a message to our school magazine. So why it cannot do it for college magazine? And he took the lead. He wrote to the governor, to all of this, and yeah, the message came. Because there is a standard procedure. So you have to dream big. If you dream big, even if that biggest thing doesn't happen, the bigger thing will happen. So so I think the day we reach to that level where Nimbus and Hillfair, they are talked about in some national or international, maybe after some time, platforms, then I think we have become really successful, and it is very much possible. I think with each year, these contests have improved. Even the Srijan magazine, each year it improves a lot. So yeah, we can definitely reach there, but that should be the aim.
Yes, with guidance like yours, it will surely be possible, and we will be on the right track with guidance like yours. So, I guess it's 9:22 here in India, and looks like we have already taken a lot of your time. You would have a lot of plans for this weekend too. So, we thank you again for your intriguing words. There was a lot to take away from this talk, and we surely learned a lot. Now, I would like to invite Arushi to deliver the vote of thanks.
Okay, thank you.
Thank you, Arsh. Please join me in a big round of applause for the chair. We had such an inclusive valedictory session. We put him in this spot because we know he always delivers the best. I know that I'm standing between you and the dinner, but I'll be feeling my duties if I don't thank everyone who helped in bringing this event to a success. First of all, my big thanks to Mr. Kumar Vijay Mishra, who spared his precious time for this interview. I acknowledge institutional contribution here in particular for providing us this opportunity to conduct this event. I highly appreciate the efforts of the interviewer, the co-hosts, and the team public relations that coordinated well to bring this event to a success. I'm also grateful to the audience who consistently sat here to gain all the knowledge and support us. With this, I will take your leave. Thank you. Have a